Just our home. It is who we are.
Welcome to Mobile Legends.
All right. Yeah, man. Let me see. I should have got my other boots. Defense.
All troops deployed.
Resting at the bottom of the sea. Bodies of
Ooh, they doubled them. They almost got it. So I got some people in the oh my goodness. As long as it's not me. Not yet. Oop,
where it doesn't belong.
There we go. Three gentlemen. Walters and Curtin.
Tides rise,
Got 5 minutes to get this done. So we need some. I'm gonna just let that ride. I got 20 seconds until my ultimate is ready. Where's my marksman? There it is. Go, 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 go. Like, I don't know. I stunned him. I don't know. I can try again. 4 seconds. Push if we can get a stun. I guess. I really want to try to pull them first. They had it. That we had to get everybody some more. Yeah. I still got a solid 5 minutes. Then we'll get the party started.
Feel the surge of the oceans.
All right. 20 seconds until that's ready.
Bottom of the sea.
Where's my marksman? Go, go, go.
Just our home.
It's like my team can't even see me up there. Like I had them good and stuff for a long time. Where they were, they might. So that like 4 minutes to run. I'm ready.
I can't see through the ocean.
3. Hopefully the biggie he's already used it up. Well, what happened? That's not what I'm gonna do. This biggie's ultimate. I'm gonna have to leave these guys. Can't finish. I was taking attendance. They got. I got. They got some trickling in. Back up, back up. I get something. Okay, that's okay. We're gonna lose. I don't know. It seems like we're missing something. Take attendance. We got a solid 2 minutes and we'll get the party started. I'm probably just gonna abandon these guys. We are definitely losing, and I don't know. With these matches, you never really know until it's over. My stuff is ready though. It's just a matter of me catching them.
This is the way.
These guys good. They're just food. Like I had most of them good and stunned, and somehow all of my teammates still died. I'm like, they are just can't get in there. Especially with them having Biggie, like that just totally undermines my effort. Let me see. What do we got? 3. There it is. What's the time? We got 1 minute. We got 1 minute to do
Don't
this.
stick your nose where it doesn't belong.
There we go.
Shut down. Double kill.
All right, I'm gonna have to bend these guys because it is that time. Essentially. Got less than a minute. 20 seconds there. I'm gonna do one more push, then we're on the show. It is that time. I got 7 seconds. Here comes Johnson. I'm waiting for him. I need somebody to stop. I need my guys. All right, well, it was fun. Yeah, I got to get going. Oh, well. All right, gentlemen. Yeah, so usually those matches take 10 minutes, and I don't really mind quitting those. I don't like to quit them, but it's like a brawl. It's like a little side, whatever, so it doesn't really, not that any of the game matters, but yeah, there's just a little demo or a sample of that game. So that game is called Mobile Legends, and I mean, I'm not using calculus in it, but I am using a lot of like frequency, timing, geometry. I am using math in it, and not calculus per se. I'm not like breaking out and doing calculations or anything, but some of the concepts as far as rhythm, timing, frequency, baiting opponents, psychology. Like these are some of the concepts that are at play, and that's just like a little sample. That's a mode called brawl mode. Okay, so I have that is that time. It's officially 6 o'clock. I've been taking attendance, so I think we're looking pretty good. I think I got everybody. Let me just check my waiting room real quick. You guys are looking good. I got a total there. Let me confirm that number to make sure I got everybody. Make sure I got everybody. Everybody. I don't know how to song goes. Anyway. Okay. So let's see. So this will serve as our last official section for chapter 3 on applications of differentiation. And we're going to be working on section 3.8, implicit differentiation and logarithmic differentiation, right? I want to give my own summary of implicit differentiation. So it's like, so far, what we've been doing, we've basically on the derivative, the official, technique definition of the derivative. And then we explore on differentiation. Again, the derivative is the slope of the tangent line at a point. And then I know we like this chapter has been mostly on applications of the derivative, but the form that it's been taken, it's always been like y in terms of x. Y is a function of x. It's always been y as a function of x. But like, what if you have a function in one variable, right? A function of x and y, right? So that's kind of like where implicit differentiation comes in. Like when you have more than one variable and you want to take the derivative, and we're going to be exploring some techniques this essentially along those lines, because sometimes we're not able to get y explicitly as a function of x. So that's where we have implicit differentiation, right? So let's take a look at it. A few objectives here. One, we want to see how to differentiate implicitly, and then we'd like to use logarithmic differentiation to find the derivatives of certain functions. So the simplest way I can kind of articulate how we do implicit differentiation, I think there's at least like 2 different techniques. The main way is like, whenever you take the whenever we're going to take the derivative of a variable, we are going to put either dy or dx, right? And then ultimately in the end, once we've kind of taken the derivative and applied the techniques that we've been talking about, product rule, quotient rule, power rule, that kind of stuff, chain rule, that kind of stuff, then we have to use algebra to shift. We want to finish with dy over dx equals what everything else on the right. All right. So again, that's the simplest way I can articulate implicit differentiation. There is another technique where the other technique I kind of struggle to articulate it. So we'll see it in action if it pops up or if and when it pops up. But this, again, the simplest way I can articulate it, whenever we take the derivative of a variable, we're going to put dy or dx. Like if we take the derivative of y, we're going to put dy. Whenever we take the derivative of x, we're going to attach a dx. And then once we finish taking the derivative, we're going to use algebra to get dy by dx on the left and everything else on the right. That's the simplest way I can articulate implicit differentiation, right? So how to differentiate implicitly? Differentiate both sides of the equation with respect to x or whatever variable you're differentiating with respect to. Apply the rules of differentiation as necessary. Anytime an expression involving y is differentiated, they're going to put dy by dx. So this is the other version that I couldn't articulate. You still so what they're saying is take the derivative like normal, but whenever you take the derivative of y, you're going to put dy by dx on the side of it, right? So it's the same thing, it's just slightly different. So dy by dx will be a factor in the result. Isolate all terms with dy by dx as a factor on one side of the equation, and then factor out dy by dx. Divide both sides of the equation so that we can isolate the dy by dx. And so this is essentially the same thing I was saying. It's just that what they're doing here, they're only writing that expression dy by dx when they take the derivative of y. The way I like to do it, if I take the derivative of y, I'm going to put dy. If I take the derivative of x, I'm going to put dx. Then through algebra, I'm going to get my dy by dx on the left and everything else on the right. So maybe we'll showcase both techniques as we kind of explore. So given this function, find dy by dx using implicit differentiation. So like notice here, you might have a hard time trying to get y explicitly in terms of x, right? If you try to solve for y, more than likely you're not going to be able to do it. So we can use implicit differentiation to find this derivative. We can find the derivative of y with respect. Okay. Oh, there it is. Okay. All right, so the pen is here. Siri, turn the heater off. Siri, turn the heater off. Thank you. It was like, I felt like I was cooking with grease. Okay, so again, with implicit differentiation, we take the derivative like normal. Again, we talked about two different techniques. I'm going to do the one that I'm more comfortable with first. Again, and that technique is, if you're just joining us, like notice if we try to take the derivative of this guy, we can't get y in terms of x, so we can take the derivative like normal. Because we can't get y explicitly in terms of x. So we're going to use a technique. We're using a technique today called implicit differentiation. The first way that we're going to do it, again, whenever I take the derivative of y, I'm going to put dy. Whenever I take the derivative of x, I'm going to put dx. And then I'm going to use algebra so that I get dy by dx equals everything else on the right. Okay? All right, so let's give it a go. All right, so for part A, let me see. So if we want to take the derivative, right? So that first one, the derivative of y to the 3 is going to be what? 3y squared. I'm going to put dy. Okay. Now with that second term, we have two things that are being multiplied. So we have to use the product rule, right? First times the derivative of the second plus the second times the derivative of the first, right? So the first is this guy. The derivative of the second is going to be 5y to the 4 dy, because I took the derivative of y, plus the second, which is this guy, times the derivative of the first, 2x dx, right? Because I took the derivative of x, so I put a dx on there. And then the last one is what? Minus 4x cubed dx equals 0. Okay. I'm going to expand this out. And what I'm going to do is any term that has dy, I'm going to move it to the left. Any term that has dx, I'm going to move it to the right. Okay. So let me see. We got this 3y squared. I guess so. Let's do this. Let's do this. So dy, okay. There's a dy, so this one is plus 5x squared y to the 4 dy, okay. Now there's a dx. I think the last two have dx. I'm going to move those to the right hand side of the equal sign. So the first one I'm going to subtract. I'm going to change the order, right? I'm going to go ahead and add that 4x cubed dx to both sides. So that's going to be 4x cubed. I guess we'll do this color. 4x cubed dx. And then this other term we're going to subtract. So we're going to have minus 2xy to the 5th dx, all right? Okay. Come on. Let's duplicate. Probably should have just got a blank page, but I'm going to work with this. I don't have to unplug you because you don't like to work when you're charging for whatever reason. Come on, back up. Okay. And let me get rid of all of this stuff, like from there to there. So this is basically where we left off, right? So then all I'm going to do on the left-hand side, I'm going to factor out dy. On the right-hand side, I'm going to factor out dx, and then just use algebra so that I can isolate dy by dx and everything else is on the other side, all right? So factoring out my dy, and also here I'm factoring out my dx. So then on the left, I guess you can write it as like dy, and then times whatever's remaining. 3y squared plus 5x squared y to the 4. Okay. And then that equals, if I factor out my dx, times whatever's left, 4x cubed minus 2x y to the 5th. Now I'm going to divide both sides by dx and divide both sides by the thing in the parentheses on the left. Right? So I'm just using algebra at this point. So now we're going to finish with dy by dx equals, let me see, so that means the 4x cubed stays on top. And we're going to divide by 3y squared plus 5x squared y to the 4. Okay. So we really didn't do, I know it may look intimidating, but we didn't do anything that different than what we've been doing so far. The only change was, whenever we took a derivative, of a term, a variable, we put either a dy or dx. All right. And as usual, if you have questions, feel free to unmute yourself to stop me to get my attention and we can talk about it. Yeah, so that's how I like to do it. For me, that's just a little bit easier. But we saw in the previous slide, they were like, you can pretty much do the same thing we did. It's just that the other alternative is, whenever we take the derivative of y, we put dy by dx. Otherwise, we just take the derivative without putting anything. Okay, so maybe we'll try their technique on another question. So we got 4x cubed, 2, 3, 5. 4x cubed. Oh, we forgot part B. Find the slope of the tangent line to the curve when x is 0 and the corresponding y is 3. Right, so they gave us a point. Basically, if we want the slope of the tangent line, we just plug that point in. It looks like it's 0. Is it flat? Because if what we have is correct, right? And when x is 0, this is gone, and then this is some number. This is a number, but this is gone. So then ultimately it looks like we're going to have 0 over some number. That's okay. So it looks like the slope is going to be 0. right? So that means that if we were to see the shape of this graph, we should be like either at a local max or a local min, or some kind of max or min, right? It looks like the slope is 0. Okay, that was an interesting one. That was fun. Let's try another one. So the quick checks I usually leave for you. For this demand equation, differentiate implicitly to find dp by dx, right? So if we were doing it the way the book does it, whenever we take the derivative of p, we will put dp by dx. Otherwise, we don't put anything, right? So I'm going to try there too. We want to find the derivative of p with respect to x. Okay. So on the left-hand side, the derivative of x is just going to be a 1. On the right, we have to use the chain rule. So first the power comes down times the inside. Then we subtract 1 from the power. Then we're going to say times the derivative of the inside is going to be what? Negative 3p squared. Then dp by dx. All right, and that's it. So then now we just want to use algebra to isolate the dp by dx. Okay. I am going to rewrite this. So at this point, what we have now on bottom, we have 2 times the square root of 200 minus p cubed, right? And then on top, we have this negative 3p squared. Okay. Let's see, that's all of the bottom. That's on top. And then we're essentially saying that times dp by dx. Okay, and that equals 1. So I just rewrote it so we can see it more clearly. So now, in order to isolate the dp by dx, we just multiply by the reciprocal. Multiply both sides by the reciprocal. So then now our dp by dx should be the reciprocal of that times 1. So it looks like it's going to be 2 times the square root of 200 minus p cubed over, and you could maybe put a negative here, 3p squared. Let me move some stuff around a little bit. Okay. So hopefully this is making sense, right? Silence to me from you all means one or two things, maybe more than two things, but at least either you're getting it or you're completely lost. And I just try to stay optimistic until I realize otherwise. So let me make sure this is correct first. That's 2 times 100. What can you factor out? 100 is what? 10, 8. Let me think about it. 16 is what? 240. 25. But it's not a perfect cube. Yeah, so I'm gonna just leave it like that. 2 square root of 200. Yeah, that's exactly what we get. Okay. So hopefully we're all aboard and we're not all bored. All right. Given this function, okay. All right. So we just saw a demo of the way the book likes to do it. I feel inclined to do this one the way that I like to do it. Now, I mean, actually, I think I'm gonna do this the way the book does it because I don't see any y values on the right hand side. I feel like they're baiting me. I feel like I'm getting baited into something. Yeah. So instead of doing all the algebra, I'm just trying to make sure. Oh, can we do something like that? Let me see. What was I gonna do? 4. What's that derivative? 4x cubed plus 3. What about that one? 15. No. I feel like there's a better way to go about this. If that were u, then we could do du. Give me just a moment. If that were u, then du would be 15. I'm just gonna take the derivative. Right? Like, let's just see if we can get it. All right, so dy by dx, right? So it looks like first we have to apply the product rule. The first times the derivative of the second plus the second times the derivative of the first. So the first is this guy, x to the 4 plus 3x minus 1 quantity cubed. First times the derivative of the second. So now we have what, a half times 1 minus 3x to the 5th to the power of a negative 1/2. And then times negative 15x to the 4. So that's the first times the derivative of the second. I'm going to kind of work down here, plus the second, which is this guy, times the derivative of the first. So then we got to use a chain rule there. This one is so messy. So first the 3 comes down. Then that means all of this gets repeated. Power of 2. And then we got to say times the inside function. Or excuse me, times the derivative of the inside function. I think that's this. Oh, okay. I was just trying to see, do we have something we can factor? And it looks like we do. It looks like they both at least have 2 of that x to the 4 term. So I'm going to factor out 2 of those, right? So then if I keep going, we got this x to the 4 plus 3x minus 1 squared. So we factored out 2 of them. So then when I do that, this guy is gone, and this guy turns into a 1. Okay. Okay, let me think. Okay. So in that first one, it looks like we have this 2 times, oops, change my color back. So we have this 2 times the square root of 1 minus 3x to the power of 5 under, it looks like this, negative 15x to the 4. Okay. And then in the second one, all that's on top. So we're going to say what? Plus, like we have 3 times the square root of 1 minus 3x to the 5th times 4x cubed plus 3. Okay, let me see if I can get some other common factor. Now I'm thinking that square root, or we could get a common denominator. If we got a common denominator, we would have to multiply the right-hand one by 2 square root of blah, blah, blah over itself. And then we can combine those together. Let's do it. And maybe we're close. Maybe we're just not giving ourselves enough credit, right? Let's just keep going. X to the 4, 3x minus 1 squared, okay? So my common denominator is this 2 square root 1 minus 3x to the 5th, that guy, okay? Now the left-hand side is going to stay as is, but the right one, let me think. We're gonna multiply, so let me say, basically like this. 2, yeah, that's fine. Square root 1 minus 3x to the 5th. And then times 3, and then times another. Hopefully I'm minimizing my mistakes because this is really easy to miss stuff. And it looks like we still got this. Let's see. And then we want to close this guy off. Let me see. So now the square root is gone because it's basically this thing squared. So that's going to be gone. Okay, let me duplicate this slide. I think we're almost there. No. Duplicate. Okay. Now what I'm going to do is get rid of this, all of this. Because I'm just picking up where we left off because I have it on the previous slide. That's why I duplicated it. Okay, so this is where we left off. So those are combined. Let me try to capture that. X to the 4, 3, 3x minus 1 squared. Okay. So now let me see. we got this negative 15x to the 4. Let me see, that's going to be a 6. Okay, all this being multiplied. So we got this plus 6. We got this 1 minus 3x to the 5th. And then we got this 4x cubed plus 3. Okay. All right. And then is that over? Okay. Okay, let's see. Can we get anything else to cancel? What happens if we rationalize? Okay, I think if we rationalize, right, multiply the top and the bottom by that square root, it's just we're gonna get rid of the fraction, right? So what I'm saying is, like, if we multiply by 1 in the form of 1 minus 3x to the 5th, 1 minus 3x to the 5th, right? When we do this, this guy is going to be gone. Wait a second. And it's going to cancel this guy. And all that's going to be left is that one radical there that we really should distribute. Actually, it's not. It doesn't go there. Wait a minute. No, it does. Yeah, we're good there. I feel like it's making it worse. But let's keep going. We're almost there. We're almost there. And I think to kind of help it, hopefully this helps, I'm going to put a 2 here like that. So that guy's gone. Let me think. And this one is gone as well. Okay, that doesn't help it. Okay. Well, that didn't change anything. Okay. So let me think. We're almost there. I know we're close. So we still have this x to the 4, 3x minus 1 squared. Now, I feel like I'm missing something. I know that I don't think they're really intended for all of this. I know that there's something that I'm missing, but I just want to finish. We're almost there, so I'm just going to go ahead and try to wrap it up. If I distribute that 2, we're going to have negative 15 over 2 x to the 4 times the square root of 1 minus 3x to the 5th. Okay. If I distribute the 2 there, that becomes a 3. We still got this 4x cubed plus 3, and we still have this square root 1 minus 3x to the 5th. That doesn't really seem like it helped us. We could factor that out. Can we combine like terms there? Or we could just not distribute it. I think I'm going to backtrack on one step. I'm going to backtrack one step and not distribute that guy and just combine like terms, and I think that's it. Right? So right here. So I'm going to leave that guy there, and I'm going to just simplify this. So that's going to give me negative 15 over 2 x to the 4 plus 3 times 4x cubed plus 3. Okay. And then we can, I'm just going to leave this over here, 1 minus 3x to the 5th. And then we can kind of like combine like terms and simplify there. Let me see. Like we can distribute that guy. I feel like there's a much simpler way and I'm just missing it, but this should be the end of this one. Squared 15 over 2 x to the 4. That's going to be what? 3 times 4 is 12 x to the 3rd plus 9. Okay. And that's a FOIL, so I'm not gonna expand that. And they probably stop. Sometimes what they'll do is they'll stop super early and they won't do all of this. Now we could FOIL out those 2 trinomials. I'm gonna put a pin right here. I want to see what the textbook did. All right, so we got it down to here. We could go a little further, but I feel like there's something that I'm missing. If that was my u, 4x cubed. Let's see what the book did. Oh, log. See, I knew it was something. I totally missed it. Right? Let me see what answer they got though. I'll go back and explain what they did. Not the quick check. Go back. Come on. Is this the same thing? Since y equals this, Let me see. They got the x to the 4 plus 3x minus 1 cubed, and they got the square root. Now they got all this extra stuff here. I feel like if we simplify it down, eventually they'll get to the same spot as we did. Like, I don't think that we're wrong. Okay. I mean, we could confirm it if push comes to shove. Like, we can confirm it. So given that y equals this, fine. Now using logarithmic differentiation, I just forgot. Start by taking the natural log of both sides, right? So if we take the natural log, the log of a product becomes the sum of the logs right here. The log of the product becomes the sum of the logs. So this log times that log. That is a lot more simple. So they just started by taking the log on both sides. Then it breaks it apart so that we're not doing the product rule, right? And so then when we go to take the derivative, it's a lot more simple to work with. The derivative of natural log is going to be, it's du over u. So it's dy by dx over y, right? And then this guy is just du by u. So it's going to be this derivative over itself, and then this derivative over itself. Okay. So that was a log technique. It just slipped my mind. I knew there was something I was forgetting. That's not one I use often, so that's why it caught me. Right? The derivative of natural log, dy by dx times 1 over y. Again, this derivative over itself right here. This derivative over itself right here. And then it's just algebra, right? And then because y equals the original thing, right? So then you just replace this y, you replace this y here with the original thing, and you're good to go. Yeah, I just forgot that technique, right? So they multiply y on both sides. So then since y equals this, you're going to have all of this on this. I mean, and that's fine. Now, I feel like if we do algebra, eventually we'll get to the same. This is one I would just argue, right? If I got an answer and this is their answer, I would just argue. I was like, okay, well, it's essentially the same. Now, obviously, they wanted us to do the natural log technique, use natural log for differentiation. But I felt like if you had this experience where you got it down to a certain point and the book has this, and if you can just show the connection between what the book has and show that it's the same as what you have, I would give you full credit for that, right? Because obviously you can do more algebra here. Let me see. If we would distribute that, it would be gone here. Like, I feel like if we do more algebra, we can connect what we got to what they got, right? But the main point here. Let me turn it off. Give me just a moment. Settings. This one. The main takeaway here was that technique of using the logarithmic differentiation. So we did the product rule, and I don't think there was anything wrong with what we did, but you saw how kind of messy it got. So if we had taken a natural log on both sides, then it would have broken up. This is much easier to work with than what we were working with, right? So I'm gonna have to put a pin in that when I come back to it. I just forgot that technique. So we just have to keep that in mind going forward, that we can use that. We have that technique at our disposal. See, and so if you take the log here, it'll separate it. So maybe that's a technique that you use. Like if you find that you have to use either the product rule or the quotient rule, and it seems like it's getting messy, then try taking the log on both sides and then take the derivative. All right, because in this example, normally it would be the quotient rule, the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. Then you have all these expressions that are nasty. But if you do the log, if you take the log on both sides first and then take the derivative, it's much easier to work with. Yeah, I just straight forgot that thing. Okay, so we'll just take that L and keep it going. Let me see. Oh, and we got time, so we'll go through some of the homework corresponding to this. Find the absolute minimum value. Okay. So the absolute minimum, so that's going to occur when the derivative is 0. So let's first find the derivative, and now that we're aware of the log technique, right? Let's start off by, because if we try to, I don't think we have a way, of taking the derivative of something like this. But if we take the log on both sides first, then I think it'll be a lot more simple to approach, right? So let's just give it a go. Okay. So we're starting. Let me see, we have this y equals, we got x to the power of x, right? So we're going to try that same technique and take the natural log on both sides. So the natural log of this guy, natural log of this guy. And when we do this, that allows this x to come down, right? So then on the left, we're going to have the natural log of y. On the right, we're going to have x times the natural log of x. Okay. So then the derivative of log is du over u. So on the left, that's going to be 1 over y dy by dx, all right, equals, and I think we do have to do the product rule, all right? So I'm just going to do it. The first, let me see, 1 over x, right? So the first times the derivative of the second. So those are just going to be x over x. First times the derivative of the second plus the second times the derivative of the first is just the 1. Okay. And then also, what, y equals x to the power of x. So then ultimately our dy by dx, multiply both sides by y. So we're going to have this x to the power of x times 1 plus the natural log of x. So we could just leave it like that. Let's see. So if we want the minimum, we would set this to 0 and solve. Let me see. Now that x to the power of x, I don't know. I don't think that's going to be 0. So I'm going to kind of put a pin in that one. But I know we can get something from the expression, that's the factor on the right. So then 1 plus the natural log of x equals 0. Okay. Yep. So then the natural log of x equals what? -1. We raise both sides to the power of e. So we're going to say e to the power of log, e to the power there. Natural log of 0 is undefined, right? Because if we set that first factor to 0, x to the power of x equals 0, and if we try to solve, like say we were to take the natural log on both sides, I think the log is undefined. Like if we try to take the log of 0, that's undefined. So there's not going to be a solution there. I could write that out if I need to, but again, let me just say that one more time. If we set this guy equal to 0, right, and then we took the log on both sides to solve, we get no solution because log is not defined for 0, right? So we wouldn't get anything there. But then the one on the right, if we keep going, so e and log are going to cancel each other. We're going to get x equals e to the power of -1. Now that's the exact result. And then we would just use our calculator. So when x is equal to e to the power of -1, let me see. I mean, it makes that 0. And then we really should do like the first derivative test to confirm that this is indeed a minimum, right? So this is our first derivative. Well, this tells us the x value, but it doesn't tell the y. So we would need to find the corresponding y when this is our x, right? Let me just use my calculator real quick, right here. Let's see this one. Yeah, I always forget that log technique because that's just not one that's like an unorthodox technique, and it's like I'm like, and I don't know why I don't just look at it in advance. I guess I like to do it on the fly. I feel like it makes my presentation more genuine versus, I mean, it probably would be smoother and better if I research it in advance, but you know, that was just I had to take that out. Okay, let me see. So what if we did? I'm going to say e to the power of -1. Then I'm going to say that. Like if here, let's do this instead. Let's go to y equals. We're going to say x to the power of x. Oh, God, you got to get out of here. Oh, well. I need to close that door. Right, so that's the original function. Hopefully it'll take it. And then I'm going to plug in, right? I want to evaluate that when x is equal to e to the power of -1. Okay. And so the corresponding y value is this approximately 0.7, right? So then, and again, we should verify that this is indeed the minimum. Like we can choose a number, x value less than this and an x value greater than this, and show that the sign of the derivative goes from what? Decreasing to increasing. Just for the sake of time, I'm just not doing all of that. Right here. Mm-hmm. So then we get an absolute minimum value of 0. I guess we'll say 6922 at x equals e to the -1. Okay, so we got something like this. Okay, well, can't win them all. Let me see. So 0.6922, let me see. So to differentiate, first we find the log on both sides. We did that. We brought that down. 1 over y, that's a 1. I think we got all of this so far. Okay. So then we set the derivative equal to 0 to find any critical values. We can ignore the factor x to the x since it's never equal to 0, right? And again, even if we tried to even if we did set it to 0 and try to solve it, when we go to take the natural log on both sides, again, log is not defined when x is 0. So then that's an indication that that's not going to be 0. I guess it would be something like 2 squared, 3 cubed, 4 to the power of 4. Okay, so it's essentially an exponential function. That's interesting. Okay, and then on the right, we get x equals e to the -1, which is that number, and then the corresponding y value. Using the first derivative test, right, we need to show that it goes from decreasing to increasing. Okay, or you can use the second derivative test. Because this is the only critical value, if you plug this into the second derivative and you get a positive result, that means the original function is concave up. So that means that this would be the minimum value. And they got the same thing we got, 0.6922. Okay. Okay, that was an interesting one. That was a fun day, right? Okay, so let's work some examples from the homework. Let's work some examples from the homework. All right, let's add a page. And let me change my view to seamless. Okay. That is correct. All right, so let's hop over to the homework and do as many as we can. We got a solid 30 minutes. Let me go like this. Let's do another window. Let's go full screen. Is that a tab? That's a window, right? Okay, that's fine. Right here. Allow. Sign in, come on. Allow. March 23rd from 1. Okay, this is calculus. And let's look at 3.8. It should be in week 10 right here. Hey, Google, give me a random number between 1 and 25. Let's start off with question 6. And actually, what I'm going to do is right here. Give me a random number between 1 and 25. Okay. So I'll just keep that in the pocket. Maybe we'll do that one next. Okay. So we're asked to maximize this function where x and y are positive numbers such that x plus y squared equals 9. Okay. Let me think. So we want to take the derivative. Let me think. And it does look like implicit differentiation. So maybe it looks like we can write x in terms of y, and then we can get b in terms of y, right? So use that second equation so that we can get b in terms of one of the variables and then take the derivative, right? I think we got a plan of action. Let me try something like what I was doing for other students. If I go, come on. I believe you. You can do it. Come on. Thank you. Oh, let's see how this works. Let me zoom out some so I can at least see it. This. So we'll take some notes here. So this is from 3.8. This is question 6. It comes from section 3.5, question 5. Okay, so it's not from 3.8. We're asked to maximize. This function b equals to 2xy squared. Where x and y are positive. And we're also given that x plus y squared equals 9. Okay. Yeah. Let me try that. Okay, so my original thought is go ahead, we can isolate one of the variables in that second equation, right? So if I isolate the x, we'll get x equals 9 minus y squared, right? And then if I plug this into the equation or the function we're trying to maximize, so then we get this b equals 2 times what? X times y squared. But x is 9 minus y squared, okay? So now we have b in terms of y, all right? Let me expand this out some. So I'm going to distribute a 2y squared. If I distribute a 2y, 9 times 2 is 18y squared minus 2y to the 4, right? So then now let's take the derivative of b with respect to y, right? So db, right? So the derivative of b with respect to y. The first derivative is what? 36 y squared? Nope. 36y. And then minus 8y cubed. Okay. Then we want to set this to 0. Because if we want to maximize it, that's going to occur when the derivative is 0. Okay. We could factor out. Let's see. Those are all 2s. What is that? 9 times 4. We can factor out a 4y. Let's factor out a 4y from both terms. So we get 4y. That's going to be what? 9 minus 2y squared. Oh. No longer have a perfect square. Okay. So we get a couple of critical values. Let me see. So like from the first, let me make sure this is right. 9 times 4 is 36. 4 times 2 is 8. Okay. So from the first factor, if we set that to 0, we get y equals 0, right? Because you get 4y equals 0 divided by 4. Let's see what happens with this second guy. Now, it looks like an upside down parabola that we moved up by 9. So we should have some zeros there. It's almost a perfect square, and I think we can treat it like a perfect square, right? If we do the following. So it looks like it can be factored if you accept a certain form, right? So we got 3 and 3 minus and plus. It looks like what? Y times the square root of 2. Right? That's because if we FOIL, the two middle terms cancel. We're going to get minus y squared times 2. All right, so I'm going to do this. So then now in this form, right, if we set each factor to 0, we what, add and divide. So we're getting like 3 over the square root of 2. Subtract and divide. Okay. So we got these. Type an exact answer using radicals as needed. Maximum value. So we get these critical numbers, right? So then we need to put these on the number line, choose a few test points, and see what's the corresponding y value. So, or I'm just gonna put it in the table, right? So we have our y versus our b, right? So we got this, what, -3 over the square root of 2. We got 0, and we got a +3 over the square root of 2. Okay. And b in terms of y is there. So I'm going to use my calculator. Actually, yeah, this view is decent. I'm going to go to y equals, and I'm going to say 18x squared minus 2x to the power of 4. Okay. And I want to evaluate that when x is, we're going to do each of these. So the first one, let's just go ahead and do 0 since that one seems simple. So when the x is 0, b is 0. Okay. Let's see when x is a negative, the first result. So actually, yeah, -3 divided by the square root of 2. Okay. That result, we get 40.5. I think we said y has to be positive, so we probably won't use that one. 40.5. And then we want to evaluate it again when that's positive. Okay. Okay. So, yep, we got our answer. 40.5. Because again, initially we said that y has to be positive. So we can't use this result. And this has the higher y value. So this should be the result there. So the maximum value of b should be 40.5. Exact result, is that right? Mm-hmm. Okay, let's cross our fingers. If that's not right, then I don't know. 40.5. Do a little dance, right? You got to celebrate these things, right? I feel like there should be questions, right? Now we got a solid, just right at about 20 minutes remaining. I want to kind of keep going to do some more. That was fun. So we already kind of did a shuffle, so we're gonna do question number 9. Let's see, right here. Let's see what we're looking like. Differentiate implicitly to find. Okay, we want to find dy by dx. Okay, not too bad. So this is question 9. This comes from section 3.8, question 5. Okay. Oh, I don't even know how I'm activating that, and I don't know how to get rid of it. How do I get rid of this thing? How did I do that? Oh, okay. I don't know. I don't know how I brought it about. I got to look up that gesture. As long as I can get rid of it. Okay. So we're asked to differentiate implicitly. Okay, that's fine. To find dy by dx. Okay. So we have this y to the 8 equals x to the 9. Okay. I think for this one, I'm gonna use the technique the way the book does it. So that means that whenever I take the derivative of y, I'm gonna put dy by dx. Otherwise, we're not gonna put it. I'm just gonna take the derivative. Right? So on the left-hand side, that derivative becomes what, 8y to the power of 7. I'm gonna put my dy by dx. On the right, that's just gonna be 9x to the power of 8. I want to isolate the dy by dx. I'm gonna divide both sides by expression in the front. So then ultimately dy by dx is going to be 9x to the power of 8 over 8y to the power of 7. Can I paste? Nope. Let's try that. Style like this. Okay. Copy. Okay, so let's try to submit that. What's the time? Let's see. Got my fraction. Okay. 9x to the power of 8. 9x to the power of 8. 8y to the power of 7. 8y to the power of 7. All right. I think we got time for one more. I think we got it here. Generate. I think let's try question 22. Hopefully it doesn't take too terribly long. Question 22. Okay. Use logarithmic differentiation to evaluate, right? So this is one of those cases where if we try to do it direct, we would have this long equation, right? Using the quotient rule. So to simplify it, we're going to take the log on both sides. It's a, man, I wish I don't know why. I was like, something's like, there's a different technique. You need to just look at it, glance at it, and you'll know it. But I was bullheaded, determined to just finish the work I had started. If I had just glanced at it, I would be like, oh, duh, take the log. Anywho, this is question 22, right? This comes from section 3.8, question 41. I'm just going to say differentiate using the natural log. Let me see. We got this x plus 3 to the power of 8 over 2x minus 8 to the power of 9. And that's our f of x. Okay. Okay. So what I'm going to do, first I'm going to change the f of x to y. All right, just so it looks familiar, like it looks like something we're kind of used to seeing. So that's going to give us, we're still going to have this x plus, everything else is, I'm going to leave the same for now. Just going to copy. I'm going to leave a little bit of space there, and I have my y. Okay. So now the suggestion was to take the what? Natural log on both sides. Okay. So then on the right-hand side, we can use the quotient rule for logs, right? So this is going to be the same as the natural log of y equals. Now, we're going to say it's going to be the log of the top minus the log of the bottom. But if we take the log of the top, we can also apply the power rule. So then ultimately, we're going to get 8 times the log of x plus 3 minus 9 times the log of 2x minus 8. Okay. So then now, if we differentiate implicitly, du over u, so that first part becomes 1 over y. Oh, and then we got to put our dy by dx. Okay. Let's see. On the right-hand side, so du over u, the derivative of x plus 3 is a 1. So on bottom, it looks like we're going to have x plus 3. On top, we're going to have 8. The derivative of 2x minus 8 is what? 2. So on bottom, it looks like we're going to have 2x minus 8. On top, it's 2 times negative 9 is negative 18. So I'm going to write it like 18 and put a minus here. Okay. Now, what was our original y? All of that. So we need to multiply the right-hand side by that. Does anything cancel? Okay. So then if we multiply both sides by y, we're going to have dy by dx equals, now our y from the beginning was this x plus 3 to the power of 8 over 2x minus 8 to the power of 9. And then we got to say times x plus 3, 8. We got this 2x minus 8 and 18. Okay, let's see. If we distribute, that's gone. Is that gone? But that's going to persist. We can probably leave it like this and call it a day. Because even if we distribute, I don't think it gets rid of. It might, one fraction might clear up, but I think the other one is going to persist. Or, yeah, it's going to persist. So let me see. That would cancel that. And that is going to get absorbed by that. I mean, we could. I think evaluate this. I think I'm gonna try this result and see if I can get if it works. Or before I submit it, just for the sake of time, I'm gonna view an example and see what form they put their final one in. Right, just so we can match the form. How many steps? Parts remaining are 9. I'm gonna go like this. Okay. I just want to get to the end. I think we got all of this. I just want to match the form that they have. Okay. I think we're good the way we are. Okay. So let's cross our fingers and go for it. Let's see. We got a fraction. We need some parentheses. Will this work? I think so. Okay. We got what? X plus 3? X plus 3? Nope, that did not work, but that's okay. Parentheses. To the power of 8. Okay, and then on bottom, we have 2x minus 8. No! I accidentally hit enter. That's okay. Parentheses, shift. 2x minus 8 to the power of 9. Okay. Then I'm going to do another set of parentheses. I almost hit enter again, trying to hit shift. Use another turn. Okay. So we got, where is it? One fraction minus another fraction. Okay. There's an 18 there. 2x minus 8. There's an 8 there. X plus 3. X plus 3. Okay. I think that's decent. All right, let's go for it. X plus 3, 2x minus 8, 8 over x plus 3. Okay. All right, gentlemen. So again, I feel like there should be questions, but that's a lot to process. But I feel like another reason I like to do it live is because, you know, as best I can, we still need to try to figure out how to, like, if we get something wrong, how to determine if we get something wrong and problem solve, and just be a little resourceful. But if you're like working in the homework or honestly on any assignment, quiz, exam, whatever, and if you get stuck like that, you know, between your resources and my resources, I'll make sure that we get to the bottom of it and we figure it out. All right. So that the goal is to try not to be fooled by the same question more than once. Right. This is a good time if you have questions. While you kind of think if you have any questions, I'm going to go ahead and make a copy of this available. I'm gonna share, send it to box. Let's get it to the right folder. 24. Traditional. Come on. Come on. Calculus. Notes. Updated daily. It should be, yes, week 10 on Wednesday. Send it there. So when this bar finishes loading, you'll receive a copy of everything that you saw me writing. And if there aren't any burning questions, we're going to go ahead and end the session here. And from one beautiful mind to another, enjoy your weekend, guys. Get some rest. You know, hopefully you are like, you have some kind of plan to kind of get through this. Either make use of my office hours, or you're working with a classmate, or you've connected with a tutor. Between one of those three sources, something should click, right? Either me, a classmate, or a tutor, right? Whatever you resonate with, or whoever you're most comfortable with. Okay, that's a reliable resource. Okay, all right, gentlemen. Good luck with everything. And again, I'm here if you have questions or if you need help. With that, we're going to go ahead and end this session here. And from one beautiful mind to another, have a great weekend, and I will meet you. So next week, we're going to be moving into our final chapter, right, on integration. And I'll give you a quick little heads up. So, you know, we've been doing the derivative for chapters 1, 2, and 3. So with the derivative, we were given a function, we take the derivative, we get an answer. Now with integration, we're going to start with the answer and work backwards, you know, using the antiderivative. So basically it's the antiderivative, right? So starting with the answer, use integration to get back to the original, right? So that's what chapter 4 is about. All right, gentlemen. Take care. Have a good weekend, and I'll see you Monday, same time, same place. Take care. Peace. Okay. Let me stop this.
All right, Professor, have a good one.
You as well. Take care.